So like I was saying, if you go to the models on the canvas, you have seen that I'm posting some videos about the FinLab or Nastran. Okay, again, it's not required from this course that you, I mean, it's not going to be graded or anything like that except for the final project. But there are editors in case you want to learn it on your own. You can open the videos. I try to make them short. That's why maybe I talk a little bit too fast, is because I know that if I make them more than 15 minutes, you probably will get tired, no? So I try to keep them always under 15 minutes. Okay? But the don't expect is that you have to watch them or learn them, because I just put them there if you want as extra stuff for you to learn. Okay? Okay, so I think the other day, I hope I brought it because, okay, yeah. The other day I brought that saying that we're going to do today this problem over here, no? And we did the figure, is that correct? Okay, so basically what we're going to do today is just solve this one. And maybe I won't do it this time in class, but I've also created a short video on Nastran on how to do this one. And it will be added, that'll probably be video 4 or something out of the film. Okay? And the reason I'm doing that, like I mentioned today, so that you can go on the you can go to CMAP to check the assignment problems, no? Okay? And all right, so here we go. So basically, I'm not going to do the figures. We have this figure here where we have a fuselage frame. This represents a fuselage frame. And there's two cutouts, one here and one here. Okay, so if you kind of look at it, it's not really the way it's studied, but the reason why I selected this one from actually Dr. Islami, that's from his notes. So I try to take the best of each one, because the best of me, I combine them. But what I like about this one, this is kind of could represent like what would be the modeling if you want, of, let's say, the windows out of a fuselage, no? If you start putting more than 2, no? Okay. In this case, it would probably more, like operators that you can have for maintenance or access different equipment inside the aircraft, no? Okay. So that's why I selected this one. It has some applications. So, all right. So we're going to use method 2. The solution of the current example follows method 2 of the previous example. So basically, what is method 2? What do? We write equation of equilibrium summation of forces equals to 0 for all horizontal and vertical members. Okay, so basically, let me just show you over here. So basically, we have all the members can have 14, 4, there will be the 2 horizontal, and then we have, horizontal would be 14, 4, 11, 1, 12, 2, 13, 3, and then the vertical will be 11, 14, 8, 10, 5, 7, and 1, 2, 4. Okay? So I'm going to put the number in, but I'm not going to go. I will try to go back to the figure, but not every single time. So let's first go and look at the horizontal members. Okay, so we're gonna look at the flange first. So that's the one we have here, 14, 4. We know that distance here is 10. Here is 40. And I don't have it here with me, but maybe I have the scan. Hold on 1 second. Maybe I can look at the scan. I know I did the figure, but I don't know. Oh, okay. So basically, you see that on this figure, I also put the direction for the shears, no? Okay. So basically, what we're gonna over here, we're gonna have 15 or 10. Oh, it's 15. So it's not 10, it's 15. So good that I can. So you can keep that figure over here if you want. So good thing actually that I can. Otherwise, I was gonna do everything different. So that distance is 15, not 10. Okay. And if we look at the shears as we define them, all right, so I'll probably do this one in detail. The ones I start going here, this one goes to the left and this one goes to the left. All right, so I have here, so we're gonna have over here Q1, Q2, and then let's go back. We have here the pin support, so I'm gonna replace this by let's say this will be uh, I'm going to use the same that he uses over here. I don't want to change too much, so it will be R2. Yeah, I'm going to change it. R1, and that one. Okay, so we have that equation. Okay, so we have that equation. What are we going to have? If we do now summation of forces equal to 0, what do we get? We get R1 plus 15Q1 plus 40Q2 equal to 0. Okay? So you see it's very simple problems over and over. Okay, so one, this will be, all right, next we'll go to thirteen, 3. So that one has actually a force over here of 2,000 pounds. Again, this is 15. This is 40. And if we look at the figure over here, what we're going to have, we need to look at the figure. So here we have the cutout and here the cutout, no? Okay? So what we're going to have over here is so, oops, hold on one second. Maybe I need to redo a little bit better this figure. Hold on 1 second. So yeah, I need to put then 13. We have here this, and this is 15 again. So I need to put another cut over here that I didn't put. So maybe we need to change these distances. This is 15. So then How much would be then the middle one? This should be then 25, no? Okay, sorry for that. So let's see. So here we have the cutout. Let's go back to the figure here. We're gonna have a cutout over here. Okay, so we have the cutout over here, but what does that mean? Is that here on top? Okay, let me do the figure here. When I look at mine, here will be Q1 over here. Here is the cutout. Here we have the other cutout. I'll show you now my figure. Okay. Oh, you can see it. Okay. So we have the Q1 here. Then we're gonna have the Q2 over here, but you're also gonna have a Q3 over here. So let me show you what I've done. Basically, this is what you get, no? Q3, Q1, Q2, 0, 0, and then maybe I forgot to put 1, and here we also, here is Q2 all the way, okay. Okay, Q2 and Q2 over here as well. Okay, so if I write down the equation of equilibrium, what do we have? We're gonna have minus 15Q1 plus, let's say, plus 25 what? Q2 minus Q3, no? Oh, reverse. Minus Q2 plus Q3, no? This one goes to the left, this one goes to the right. And then what are we going to have on this one? Minus 15Q2 plus 2000 equal to 0. So let's see, this will give us what? This will give us, so let's say, minus 15Q1 minus 40Q2 plus 25Q3. This should be equal to negative 2000. This will be our equation 2. Okay, next we'll go to the stiffener, to the member here. Maybe let me add some more notation here. This will be stiffener or flange 14, 4. Stiffener 13, 3. Next, I'll go to stiffener 12, 2. So basically, I'll come over here. And this one is we have here, and then let's see what we're gonna have now, the cutout. So we have a cutout over here, and a cutout over here. And what are we gonna have? We're gonna have here Q3. Now all this stuff here will be actually Q4. This will be Q5, and this one has no forces. So what will be the distances? This is 15. This distance here will be 25, and this is again 15. So what do we do once again? Equation of equilibrium. Summation of forces equal to 0. So that, what is that going to give us? Minus 25 q sub 3 plus, how much was it? So plus 15, so plus 40 q sub 4 plus 15 q sub 5. Oh, I forgot something here. What did I forget here on this one? For this section? I should have done the same thing as over here, no? So what do I forget here? Maybe let me just rewrite it. Sorry for that, guys. I mean, it's fine. We just need to add one value. So it's just because I had this one. So let's just do this part over here. If I go from here to here, what do we get? 15 q sub 4. Now I'm going to look at the section from here to here, no? That's what I did a mistake. So that should be what? Plus 25 of what? Q4 minus Q3. Yeah? This goes to the right, this goes to the left, no? Okay? Plus the 15Q5 equal to 0. So basically, if we please do this one, what do we have? We have minus 25 Q sub 3 plus 40 Q sub 4 plus 15 Q sub 5 equal to 0. And we can call this equation here 3. I mean, any question so far? Do you follow? It's basically just static stats, no? For each member. Okay, and the last one that you can do all the horizontal here will be stiffener. (11.1). Okay, so let's see what we have for 11.1. So 11.1. We're gonna have here the reaction force R3. Then what do we have? We have over here Q4. Oops, actually goes on the opposite direction. Sorry for that. It's going that direction, Q4. You go to the left, okay? And Q5 is also going to go to the left. That distance will be so the same as before, 15, 25, where all this distance would be 40 and 15. So if I do summation of forces, equal to 0, what do we have? We have R3 minus 40. Here I do 15 plus 25, 40. Q sub 4 minus 15 Q sub 5 equal to 0. And this is going to be our equation 4. Yep.
What is stiffener 14.4 has a vertical reaction but not 11.1?
Okay, so if we go to, I think the question is because here we have the supports.
Oh,
Okay, support here, and these ones don't have it. Okay, this one we are here the 2000. Does that answer the question?
Yeah.
Okay. Okay, so we did this one over here, 13.3, 12.2, 11 this one. Now we're gonna do 14.11, 10.8, 7.5, and this one over here. Okay? All right, so we did the horizontal members. Okay, since I have the figure over here, all right, if you look at the figure, how many unknowns are we gonna have? Q1, Q2, Q3, Q4, Q5, R1, R2, R3. So that will be, how many would be 5 plus 3, 8, no? So that means that we need 8 equations. All right, so far we have 4, halfway, no? Okay. Okay, so we did the horizontal members. Now we're going to look at the vertical members. Okay, so let's look at stiffener. (1411). So I do it this way. Before, maybe I do one more. (1411). So this one, what is gonna have? We're gonna have here the R2. Okay, you need the figure if you really want to understand this. Then we're gonna have here, there's a cut right here. And another panel up here. So what are those distances? I think this is 7 inches. This one is 8 inches. And this one is 5 inches. Let's see if I put that on the original figure or not. Yeah, I put on here 7, 8, and 5. Okay, so if you look at the figure, what we're gonna have here, we're gonna have the Q1 going down and the Q4 going down. So we're gonna have here Q1, Q4, and here we had a cut up, no? All right, so we do again summation of forces. Equal to 0. What is that going to give? It's going to give us R2 minus 7Q1 minus 5Q4 equal to 0. So this will be our equation 5. Okay, we keep doing the same thing. We're going to look at the stiffener 10.8. So this one's the one that's a bit shorter. So then 8. So we need to be careful for this one because we have here this. We have it cut out over here. We're gonna have Q1 on this side, Q2 on this side, Q3 on this side. No, I hope you have the figure in front of you. Again, I cannot do this every single time, but you will get it from here, no? Yeah? Is remember here 10/8. Okay, so let's see, what were the distances? This was 7 inches, and this one we say was 8. So we do summation of forces equal to 0. So what is that going to give us? 7 Q1 minus Q2 minus 8 Q3 will be equal to 0. And that should be our equation 6. All right, almost there. Next one will be stiffener 7.5. So that's another time, that's another short one. Seven, 5. So you look at the figure. Let's go back again to the figure. Now we're talking about this one here, no? 7.5, we have the force here of 1,000, no? 1,000, cut out over here to the right, then so you should have Q3, Q4, Q5, cut out. So I think cut out over here. Q3, Q4, Q5, okay. We have Q3. Was it up or down? Up, no? Q4, and then Q5 is going down over here, no? Q5. Then here we have the dimension, I think 8 inches, 5 inches. And we have the force of 1,000 pulling down over here. We have the 1,000 pulling down over here. So this is going to give us summation of forces equal to 0. Will give us what? 8 Q3 plus 5 factor of Q4 minus Q5 minus 1,000 equal to 0. Or this will give you what? 8Q3 plus 5Q4 minus 5Q5 equal to 1,000. And this should be this equation over here. Okay, equation 7. So what do we need? Only one more. So the last stiffener we need to do will be stiffener for 1,4 or for 1. Here we go. So we have here this one is long over here. We have the cutout over here. We'll have Q2 on this side. We'll have Q5 on this side. We have a 3,000 here at the bottom. And that's about it, no? This is 7 inches. This is 8 inches. And this is 5 inches. So at the end, what do we get over here? Summation of forces equal to 0 will give us what? 7Q2 plus 5Q5 minus 3,000 equal to 0, or we can get over here 7Q2 plus 5Q5 equal to 3,000. And this should be our equation 8. Okay, so basically now what do we say that we're doing all these stuff? Now we have, so we have 8 equation. What are the unknowns that we have? We have R1, R2, R3, Q1, Q2, Q3, Q4, Q5. So how many unknowns is that? 8. So 8 equations, 8 unknowns. What can we do? What can we do? Go and solve it. Okay. So at the end, so solving the below system of equations with MATLAB. I think the other day we did one example in class, no? Yeah. Okay, so maybe I'm gonna let's redo let's do the matrix A together here. So let's say we're over here, R1, R2, R3, Q1, Q2, Q3, Q4, Q5. Let's say it will be our matrix A, and I think we call this one the matrix B, the vector B. So hopefully I don't make it too crowded. So if we look at the first equation, let's go now to our pages. So we look at the first equation. What will be the first row on the matrix? What is the coefficient here? Let's do the first two together and then we'll do it faster. What should be the coefficient over here? 1. Do we have R2? 0. R3, 0. Do we have Q1? Yes, 15, no? And 40. And then what do we have? All these one will be 0. And then the right-hand side, no, that's it. So it will be 0, no? So I'll put over here, the first one will be 0 as well. Now, the second equation, try to do on your own, will be what? What should we have for R1? R1, R2, R3 will be 0, no? We have 0, 0, 0. Q1 will be minus 15. Minus 40. 25. 0, 0. But this time the right-hand side should be equal to negative 2,000. Okay, we do now the equation number 3. So what do we have? We have R1, R2, R3 are 0, 0, 0. So 0, 0, 0. Do we have a Q1? No. Do we have a Q2? No. Do we have a Q3? Yes. Minus 25. 40 Q4. 15 Q5. The right hand side is 0. Equation 4. 0, 0, 1. 0, 0, 0. Minus 40. Minus 15. And 0. Do you follow? This is not complicated, no? To the matrix. Equation 5, which is this one here. All right. So it's not R1, but it's an R2, so it should be 1, no R3. Negative 7Q1, Q2, Q3, negative 5Q4, 0, and the right hand side is 0. Okay? This one is R1, R2, so this one has only component Q1, Q2, Q3. So we have R1, R2, R3, 7Q1, minus 7Q2, minus 8Q3, 0 and 0. And this is equation 6, no? Yep. So equation 6, the right hand side is 0. I'm running out of space here, so it's fine. I'll make it work. 7. All right, we don't have R's, so 0, 0, 0. We don't have a Q1 or Q2. We have 8 Q3s, 5 Q4s, minus 5 Q5s, and this right hand side is equal to 1000. And finally, Q8, no R1, no R2, no R3, no Q1, 7 Q2, no Q3, no Q4, 5 Q5s, and this should be equal to 3000. Okay, so basically what we have here is the system A times the unknowns equals to B. So we can say that the unknowns, which are what? R1, R2, R3, Q1, Q2, Q3, Q4, Q5. Will be equal to what? Will be equal to A inverse times B. So this is going to give us that 1, 2, 3, 4, 5, 6, 7. And okay, I have 8 lines here, I guess. We're going to give us R1 equal, R2 equal, R3 equal, Q1 equal, Q2 equal, Q3 equal, Q4, Q5. So we do that in MATLAB. That is supposed to give us minus 11,550 pounds. 4,000 pounds, 550 pounds, minus 527.5, minus 90 0.94. This will be pounds per inch. Pounds per inch minus 382.0 pound per inch minus 61.5 out per inch, and Q5 minus 472.7 pound per inch. Finish copy this spring. I think that's when I changed this one. Yeah. Okay, so I solved this problem here with MATLAB. I did that last week, so I don't remember exactly how I did it, but I did the fee map, so hopefully you can still copy the results. So I did this model. Probably we'll do a video again to show you to do this very quick, but let's just look at the shears. So F5 deform total shear force. Okay, so it's here. Okay, let's look at the criteria. So I don't know. Let's look at which one is Q1 for us. Let's look at Q1 and Q5. Okay. So the two corners, so we can check. So say Q1, Q5. So what do we find for Q1? 527.5. So let's see what we have on the final element. Okay, about 505. So a little bit off because of the mesh size, no? It's about the same order. So you see, it can help you check more or less the same order. And Q5, this is giving us minus 445. What do we have over here? About 472, no? Okay, so it's not going to be exactly the same, but at least it will tell you if you're on the right order or not. Okay. So now what we could do is, which it takes a lot of time and it's not that difficult, but I could ask you what is the load distribution on each one of these members, no? Okay, looking at the actual load. So like I told you, this is not my example, this is Dr. Islami, so I'm going to show you his results. And that way you want to do in more details. If you want, you are more than welcome to copy them. Oops, hold on, sorry. To copy them, or they will be on the video online if you want to take more details. But basically, I just want to keep them here for about whatever, 30 seconds. If you want to take a picture, but you're not, you can do it. Otherwise, you can just go later to the video recording and write these distributions. Is that okay? All right, so this is what you get for these ones here. And so that's it for this. All right, so 1, 2, page 1, 2, 3. And 4. Down. Okay, so let's just go over here like some simplified observation. For shear flows. Okay, and that's the reason I do this is because I think it was a couple of semesters ago, I received a question, which was a good question, but it was valid. So the first one, let's say like shear flow approximation. In, let's say on a wind box, or can be a frame, whatever you want. But let's do here a small figure. Let's say you have a wind box. So let's say you put whatever, 4 elements. You wear them together. Here you have a panel, okay? And let's say the depth of the panel, they don't really talk about height or aerospace structures, talk about the depth of the panel. Let's say it's H, but let's say here there's a force, there's a shear force B. This is the shear force. Okay, so this is really what is happening, okay, on the assumption. That was the, if you need to calculate the shear in this wind box, as they say here on the panel, what would be your approximation? Right. It should be equal to what? What are the units for Q? Force per unit length, no? So what would be the amount of force being applied to this per unit length? Basically, if you think about it, okay, then just look at observation. For what we have learned, what will be the members that will be resisting this force? So it should be the two members that are in the same direction as the force, no? So if we want to think about it, if we think about it, we have this one here, no? This one should be resisting, and this one will also be resisting, no? So really, we have to look at what will be the amount of the force here. If you want Q, what will you have over here? So it should be what? 2Q if you want. Let's say. Let me do it a bit differently. So 2Q times H should be equal to V, no? If we do summation of force equal to 0. All this will give what? That Q should be equal to what? V over 2H, no? Does that make sense? Okay, minutes. Okay. The next one is shear flow for a curvilinear cross section. So this time, and I think you should have studied this, okay? So I'll probably do the derivation, but what is the equation that you might remember or not? So maybe recalling, I'll probably derive it later on, but let's say recalling from What is structures one? Is it AE318? No, this is 14. 318, no? 318. Maybe some of you remember that equation. What should be the, wait, let me write it down. Did you derive that equation over here? Moment equals to 2AQ for actually probably to solve exactly this problem here. Probably you solve this problem, I'm guessing. Okay, multiple times. I will rederive this equation later on, but this is basically what you had. Okay, so the good thing about this problem is that they were like statically determined. Okay, now in structures 2, the biggest difference is that almost all the structures that we're going to be studying will be what is defined as statically indeterminate. So I don't know, I mean, you should have, but I don't know if you have done it. What is the difference between statically determinate and statically indeterminate? Look at the word, the words. Statically determinate. What does that mean? What do you think it means? Yeah.
Statically determined means a structure that is like stable, essentially.
Okay, the other one is also going to be stable, but basically, statically determinate means that you can find all the unknowns just by looking at the static equations. Okay, at the equation of the okay, now what do you think does statically indeterminate means? That the static equations of equilibriums are not sufficient in order to solve the problem. Okay, so since you have a good comment over here, let's think about just to discuss here just about stability. I mean, this figure over here, and it was the same thing in statics, to tell you the truth, but what happens is that they don't tell you. I mean, it's not stable or unstable. Is this structure over here stable? Statically, it should be stable, no? Correct? Now, if I do exactly the same structure here, but let's say this time I put another member over here. Is this structure going to be stable? Yes, no? No different style, nothing to do with stable or unstable. But what is the biggest stable here is that this one will be statically determinate. So basically saying that summation of forces equal to 0 and summation of moments equal to 0 are sufficient in order to solve this problem. But now what happens if you have this one here? This one will be statically indeterminate. Meaning what? Summation of forces and summation of moments equal to 0 are not sufficient. So what you need here plus you're going to need some additional equations or equations, no? So in this case, maybe you have done it. Maybe you have done it on structures 1 or no. What would be the extra condition? Generally, you will find it from geometry. What is the extra condition you can find over here? Maybe you did it. I don't know if you did or not, but what should be something happening to this structure? Let's say I put here force V. What would be that extra condition? Is that the angle of twist of this cell over here should be the same as the angle of twist of this cell. Yeah? Okay, so that will give us an additional equation, no? Okay, basically by looking at the geometry. Have you done that one in structures 1? I don't know, I mean, it's...
Yeah.
Okay. All right, anyway. Okay, so that's what we'll be doing next. So now we're going to become a low motif. So before we start the equation, I printed this. And again, I'm going to give you time this time, yes, to copy it. Okay. So you can write, you can call this period here sign convention. So if you want, you can do both of them or just one of them. You can take a picture, post it, I'll give you about 4 minutes to copy. Basically, the other thing we're going to change right here is that instead of being S, we're going to call this VY. This will be VX. And that's it. The other called P, so this should be VY. You want to copy this one, VX, VY, VX. So basically, it's nothing rocket science. Is what do you have? Counterclockwise, positive, no? All right. So we can take a picture. Counterclockwise will be positive, and then the normal sign convention for X, Y, and Z. All right. So again, I'll give you until 21. This is important. Do it because all the equations are going to be given are going to be based on this sign convention over here. I can zoom as much as it's going to let me zoom. Did you move out of the screen or is that good? You have to, I can maybe zoom a little bit more. Or is that too much? Or, okay, you went crazy. Okay, so it's right. So that will be it. Okay, the reason being is because generally when I teach structures, okay, I teach also structure for in solid mechanics, statics, also teach introduction to machine design for mechanical advanced machine design. But for the aerospace, I also would like to do it, but the learning gets too much complicated. In structures, I don't generally like to talk about positive or negative. Really, in structure, we should be talking about what? Tension for positive and compression for negative, no? Yeah? And I think it's a lot easier to find the sign when you look at the structure, making common sense, is this member in tension, is this member in compression, than having to trust the equations. But what happens is that the equations are complicated enough here that you can lose sight of the really what is happening physically. Okay? But if you want, let's look at something here, okay? We didn't do it here, but for example, all this structure here, let's look at the member here, 14, 10, and 4. This member here should be what? Let's look at this one, 14, 4. I understand it should be tension or compression due to this loading. Should be in tension because this is going to bend, so this is going to pull out, no? Yeah? The member 11, 1 should be tension or compression? This one is going to be then in compression, no? Yeah? So, but like I say, in aerospace, the problems get complicated enough that sometimes you need to trust the mathematics. Okay, so 2 more minutes. Do you need more time to copy these figures or you got them? You got it? Anyone needs more time? No? Okay, so here we go. All right, so analysis of multi-cells in structures. And
Can you possibly zoom down?
yeah, I guess I need to zoom out now. Yes. Okay, so what could be a multi-cell? It's like the one I just did before you want. But maybe let's do it a bit more extreme. I mean, I'm just gonna do the same as before. Why to make it more extreme? It's fine. So this will be the multi-cell structure. Okay, and something I'm not gonna spend time now. I'll redo a little bit of this after we're done with this, but every time you do complicated structure, generally what you do, you try to simplify it. So we do an idealized structure. So basically we can replace this structure here by little different areas over here. So personally, I go where here you have the panels, you still have the panels. And something different that I do from other faculties because I use the English notation instead of the other notation, but basically, so instead of talking areas, I talk about booms, areas. So basically, you can replace this one by, so let's say B1, B2, B3, B4, B5, B6. So if you want, this is the real structure. And I think I've done a little bit of this again in, what is the name of this structure here, over here? Idealized structure. Have you done that in structures one? Okay. I go at the end of this chapter, I'll go a little bit about how you go from here to here, okay? But right now, they just learn the procedure because the procedure. Okay, so for the sign, convention, previously defined, Q is equal to, probably you have seen that equation as well, but I don't know, minus dx ix, this is an ugly equation, minus vy ixy divided by ixx iyy minus xy squared times integral 0 to s tx ds plus summation of the areas b sub r x sub r. So this is only half of the equation. So continuation minus vy iyy minus vx ixy divided by ixx iyy minus I square xy times integral 0 to s t y ds plus the summation of b sub r y sub r and not over yet because this is something that I do different, for example, than other instructions, plus q sub naught. Okay, so what is R? R is what is the number of bricks, no? It's like an index. Okay. So all right, so let's put here some legends. So what is T? T will be panel or plate thickness. In the British books, they call it actually web, but I mixed the notation. Okay. B sub R is the equivalent stiffener area. Vx, Vy will be the shear forces. All the different i's will be the area moment of inertia. We always ask that in all my classes because you do it all the time, but some of you do not really know what is the meaning. What is the physical meaning of the moment of inertia? Physically, what does it mean? I mean, you find it everywhere, no? In structures. Why? What do you mean? I mean, something also you find before finding the moment of inertia, generally what you need to define first, the center of gravity, no? If somebody asks you what is the center of gravity, some of you probably, most of you know how to give an answer. What is the physical meaning of the center of gravity? What happens at the center of gravity? If you grab an object by the center of gravity, what's happening at that point? It balances, and if I take it here, what's gonna happen? So basically it's the point where there is no rotation, no? You want it balanced, okay? Until what time do you have class for 30? Already? I'll go fast. So basically the moment of inertia is you have in every single equation is the physical meaning is the resistance of an object to rotate about one axis. Okay? So moment of inertia is resistant to rotation. Okay? If you want. All right, so we stop over here, but yeah, we stop over here. We don't have time.